Chapter 2.1, Angles in Standard Position. A note, your calculator needs to be in degree mode for this chapter. So if you have TI, to put it in degree mode, you're going to go mode, down to where it says radians degrees, over to highlight degrees, hit enter, and then you can hit exit. And you can check to make sure that you're in degree mode by doing sine 90. It should equal 1. If it equals 1, you're in degree mode. For Casio's, when you're in the calculating screen, you're going to push Shift Menu, go down to Angle. When you're on Angle, F1 will say DEG. For degree, you push F1 and then hit EXE. And again, you can check this by doing sine 90, which equals 1 when you're in degree mode. Angles in standard position. The Cartesian plane is divided into 4 quadrants by the x and y axes. An angle is in standard position when the initial arm starts on the positive x-axis and its vertex is at the origin. The terminal arm rotates counterclockwise from the initial arm to give a positive angle. We see an example here. We have the initial arm on the positive x-axis. We have our vertex at the origin, and we have our terminal arm, which has rotated counterclockwise. So this would give us a positive angle. Looking at the angles that we get in the 4 quadrants, in quadrant 1, we have angles between 0 degrees and 90 degrees. So theta is greater than 0, but less than 90 degrees. And each of our quadrants in the Cartesian plane is 90 degrees, so we can figure out what angles we can have in each quadrant. Quadrant 2 would be greater than 90 degrees. Theta is greater than 90 degrees, but less than 90 plus 90 is 180 degrees, which is the angle of a straight line. If we measure from here all the way to here, straight line is 180 degrees. Quadrant 3 starts at 180 degrees. It's greater than 180 degrees, but less than, what's 180 plus 90 gives us 270. And then quadrant 4 would start at 270. Angles in quadrant 4 would be greater than 270 degrees, but less than 360 degrees, which is all the way around. The x-axis would be 360 degrees, just like the degrees in a circle. And then on the axes, the x-axis would start at 0 degrees. The y-axis, the positive y-axis, would have a value of 90 degrees. The negative x-axis would have a value of 180 degrees. The negative y-axis would have a value of 270 degrees. And then when we get back to the positive x-axis, our angle measure would be 360 degrees. Reference angle. The reference angle is the acute angle formed by the terminal side of the given angle and the x-axis. There is a reference angle for every angle in standard position. So this image shows us that in quadrant 2, we have this angle in standard position. It's 120 degrees, and the terminal arm ends in quadrant 2. And then it tells us that this measure here is 60 degrees, and that's called the reference angle. That's the acute angle. Remember, acute means theta is less than 90 degrees. So this is the acute angle formed between the terminal arm and the x-axis. If we didn't know what the reference angle was, and we were asked to find the reference angle for an angle of 120 degrees, we know that the Negative x-axis is 180 degrees. So if we take 180 and subtract the angle of 120, we get our reference angle. Theta r equals 180 degrees minus 120 degrees, which equals 60 degrees. Let's look at when we have an angle in standard position that has a terminal arm in quadrant 3. We can write the angle measures at each axis: 0 degrees, 90 degrees, 180 degrees, 270 degrees. For this one, our reference angle is part of our angle, whereas this one over here, our reference angle was after our angle. So we have to do the math a little bit different. If we want to find the reference angle, if we didn't know that it was 60, but we knew that our angle was 240, in this case, we need to subtract the portion of our angle that is in quadrants 1 and 2. So subtract 180 from our angle to get our reference angle. Theta r equals 240 degrees minus 180 degrees, which equals 60 degrees. And let's look at one that's in quadrant 4. Our angle equals 315 degrees, and we're told that our reference angle is 45 degrees. We can write the angle measures at the axes. We have 0 degrees, 90 degrees, 180, 270, and then 360 when we go all the way around and get back to our positive x-axis. The angle plus the reference angle is 360. So if we start at 360 and subtract the angle that we know, then we'll get what's left, which is the reference angle. So to calculate the reference angle, when given an angle that has a terminal arm in quadrant 4, you start with theta r equals 360 degrees, and you subtract the angle, which is 315 degrees in this case, and you get 45 degrees. Determine the reference angle theta r for each angle theta, sketch theta and theta r in standard position. First one is theta equals 75 degrees. Starting at the positive x-axis, our initial arm is there. Vertex of the angle is at the origin. This is 90 degrees. Our angle is 75 degrees, so it's going to be a little bit less than that. It's going to be somewhere around here maybe. When we have angles in standard position with terminal arms in quadrant 1, if the angle we're given is acute, so less than 90, then that angle is also equivalent to the reference angle. So in this case, theta equals theta r, which equals 75 degrees. Because remember, a reference angle is the acute angle created by the terminal arm and the x-axis, which in this case is the same as theta, which is 75. Next one, theta equals 240. We know this is 0 degrees, 90 degrees, 180, and 270. Our angle starts on the positive x-axis. Vertex of the angle is at the origin. 240, it's bigger than 180 and smaller than 270, and it's closer to 270 than it is 180. So it's maybe about here. So this angle all the way around is 240 degrees. Our reference angle would be the angle formed between the terminal arm and the x-axis that creates an acute angle. So right here, we need to determine what that would be. The theta r is part of theta, so we would need to subtract from theta to get theta r. So if we start with theta r equals, start with our whole angle, which is 240 degrees, subtract this portion here, which is 180 degrees, and that gives us 240 minus 180 is 60 degrees. So theta r is 60 degrees. Determine the angle in standard position when an angle of 60 degrees is reflected, A, in the y-axis. Let's draw our angle 60 degrees in standard position. Initial arm starts on the positive x-axis. Our angle is 60 degrees. We know that the positive y-axis is 90, positive x-axis is 0, so it's somewhere in here, and it's closer to 90 than it is 0. So it's approximately here. And this is 60 degrees. Then if we reflect it across the y-axis is here. So if we reflect it across there, it would look something like this. I'm going to draw it with a dotted line just so it looks a little different. And the reference angle would be the same. So this angle here would still be 60 degrees, which is our theta r. We want to determine the angle in standard position. So what we want to know is what is this angle here, which is theta. We know theta r, and for an angle that has a terminal arm in quadrant 2, theta plus theta r has to equal 180. So theta equals 180 degrees minus theta r, which means theta equals 180 degrees minus 60 degrees, which means theta equals 120 degrees. Part B, we want to find the angle if we were to reflect our initial angle of 60 degrees in the x-axis. Let's draw our initial angle again. And if we reflect it across the x-axis, then it would reflect down, so it would look something like this. Our reference angle is still the same, so this is 60 degrees. And then we're trying to find the angle, theta, which would go from the positive x-axis all the way around to our terminal arm. The angle plus the reference angle add up to 360. So to find theta, we start with 360 degrees and we subtract theta r. For this example, that's 360 degrees minus 60 degrees. So theta is 300 degrees. Part C, if we reflect angle 60 degrees in the y-axis and then in the x-axis. So we have our angle 60 degrees, it's about there. We reflect first in the y-axis, so across the vertical axes, and we get an angle, a terminal arm over here. And then we reflect that terminal arm across the x-axis. So it's going to end up down here. It'll look something like this. Our reference angles stay the same the whole time. So this reference angle, theta r, is 60. And even when we reflect down, this reference angle still stays 60. Then we want to determine the angle theta, which goes from the positive x-axis to the terminal arm that's in quadrant 3. We know that the negative x-axis represents an angle of 180 degrees. When we have a terminal arm of an angle in center position that is in quadrant 3, our angle theta equals 180 degrees plus the reference angle theta r. So theta equals 180 degrees plus 60 degrees in this example. So theta equals 240 degrees. Special triangles. We recall SOHCAHTOA from Math 10C, where sine theta equals opposite over hypotenuse, cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent, and we can only use these for right triangles. Below we have an isosceles right triangle with leg lengths of 1 unit. Isosceles triangles have 2 angles that are equal and 2 sides that are equal. So it says we have leg lengths of 1 unit. That would be 1 here and 1 here. Those are the legs of the right triangle. The other side, the side that's across from a right angle, that's the hypotenuse. We can determine the length of the hypotenuse by using Pythagorean theorem. A squared plus b squared equals c squared. C is the hypotenuse, so we have 1 squared plus 1 squared equals the hypotenuse squared. 1 squared is 1, so we have 1 plus 1, which is 2, equals the hypotenuse squared. And then we want the hypotenuse, not the hypotenuse squared, so we square root both sides, and we get the hypotenuse equals the square root of 2. So we can write that on our picture. Hypotenuse is square root 2. Then if we want to write the trig functions for the acute angles in this triangle, notice the 2 angles are the same. The 2 acute angles are the same because it's an isosceles right triangle. So those have to be 45 because we have a right angle of 90. All 3 angles need to add to 180. 90 plus 45 is 180. So sine 45, sine is opposite over hypotenuse. We can go from either angle because it will be the same, but I'm going to go from this one. This would be my opposite, and this would be my adjacent. Sine is opposite over hypotenuse, which is 1 over square root 2. Cos 45, cos is adjacent over hypotenuse. Adjacent in this case is also 1 because this is an isosceles right triangle, so 1 over square root 2. And then tan is opposite over adjacent, which in this case is 1 over 1, which just equals 1. So this is our first special triangle, and you need to know this. You need to know how to create this triangle. So you need to know that one of your special triangles is a right triangle with leg lengths 1, acute angles 45, and then you could always calculate the hypotenuse or just memorize that it's square root 2. The second special triangle you need to know starts as an equilateral triangle with side lengths of 2. Equilateral triangles have all 3 sides are equal to each other, and all 3 angles are equal, and they must equal 60 since they need to add to 180. Then if we cut this equilateral triangle down the middle, we get a right triangle with one acute angle of 60. The other acute angle would be 30 degrees, because again, we cut it down the middle. This angle at the top would divide by 2, become 30. We could also see that if we add 90 and 60 and 30, we get 180. The bottom side now becomes 1 because we cut the side length of 2 in half. And then we can find the other side by using Pythagorean theorem. We have a squared plus b squared equals c squared, where c is the hypotenuse. Our hypotenuse is 2. So we know one of the sides, we'll call that a. We have a squared plus b squared equals, our hypotenuse is 2 squared. 1 squared is 1. Plus b squared equals 2 squared is 4. Subtract 1 from both sides, and we get b squared equals 3. And then we want b not b squared, so we take the square root of both sides to get b equals the square root of 3. So the length of this side here is the square root of 3. Let's look at the trig functions and the value of the trig functions for each of the acute angles in this special triangle. We'll start with angle 60 degrees. I'm going to redraw the triangle down here. $60 degrees, 30 degrees, a right angle, hypotenuse is 2. The side adjacent to 60 is 1, and the side adjacent to 30 is root 3. Let's look at our trig functions for 60 degrees, sine of 60 degrees. So label our sides from 60. Opposite would be root 3, and adjacent would be 1, and then our hypotenuse is 2. Sine is opposite over hypotenuse, so sine 60, opposite side is root 3 over hypotenuse is 2. Cos 60 degrees is adjacent over hypotenuse, which in this case is 1 over 2, and tan 60 degrees is opposite over adjacent. In this case, that's root 3 over 1, which equals just root 3. Now let's look at the trig functions for the other acute angle, 30 degrees. I'm going to redraw my triangle so that angle 30 is the angle of elevation. We have 30 degrees as the angle of elevation, 60 degrees in the top, 90 degrees. Our hypotenuse is 2. The side adjacent to 60 is 1. And the side adjacent to 30 is square root 3. Sine of 30 degrees. So label our sides based on angle 30, opposite, and adjacent. Sine 30, opposite over hypotenuse. Opposite is 1 here. Hypotenuse is 2. Cos 30, adjacent over hypotenuse. Adjacent is root 3 here. Hypotenuse is 2. Tan 30, opposite over adjacent. Opposite is 1 here, and adjacent is root 3. There's our trig functions for theta equals 60 degrees and theta equals 30 degrees. You might notice that sine of 60 degrees is root 3 over 2, and that's the same as cos of 30 degrees. And then cos of 60 degrees is 1/2, which is the same as sine of 30 degrees. And for tan 60 degrees is root 3 over 1, and tan of 30 degrees is 1 over root 3. So they are reciprocals of each other. You need to know this triangle just like the other one. The pendulum arm of a metronome is 10 centimeters long. For one particular tempo, the setting results in the arm moving back and forth from the start position of 45 degrees to 135 degrees. What horizontal distance does the tip of the arm move in 1 beat? Give an exact answer. If you don't know what a metronome is, you've probably seen them in movies. That's actually the only place I've ever seen them. They're usually on like a wood background, I would say, and then in the center there's like a stick that's attached, and then it just swings back and forth. So it swings like over here and goes back and forth and goes tick 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 as it moves back and forth. This pendulum arm is 10 centimeters. For one particular tempo, the setting results in the arm moving back and forth from 45 degrees to 135 degrees. Let's draw that. An angle measure of 45 degrees is halfway between the two axes in quadrant 1. So something like this. And our arm length is 10 centimeters. Our angle is 45 degrees. Then it swings to a position of 135 degrees, which we know is in quadrant 2 because the positive y-axis is 90 and the negative x-axis is 180 degrees, so it's somewhere in between those. To find out more precisely where it is, we know it's in quadrant 2, so to get theta r, we start with 180 degrees and we subtract the angle in standard position, 135 degrees, which gives us theta r equals 45 degrees. So again, halfway between our two axes, this time in quadrant 2, this is 45 degrees, and measure of the angle in standard position is 135 degrees. The arm is still 10 centimeters because it's the same arm. And then the question, what is it asking for? It says, what horizontal distance does the tip of the arm move in 1 beat? Give an exact answer. So horizontal distance from the tip of the arm in each position. That's what we're trying to find. That would be our x centimeters is what we want to know. How are we going to do that? Well, we just did these special triangles, so probably we're going to be using one of those special triangles. So can we find the measure between these two arm positions? We know that this is 135 and this is 45. So if we subtract those two, then we'll get this part between the two arm positions. 135 degrees minus 45 degrees, and that gives us 90 degrees. So this triangle that we have in our picture is a right triangle. And what kind of right triangle is it? The two arms are both 10 centimeters. So that means that it is an isosceles right triangle. And what we know about isosceles right triangles is two sides are equal and the two acute angles are 45 degrees. Because the angles have to add to 180, we have a right angle, which is 90, so we need 90 more, and each of our two acute angles has to be the same. 90 divided by 2 is 45. So what we really have is a variation of one of our special triangles. Our arm lengths are 10 centimeters. Our angles are 45, 45, and 90, and we're trying to find the hypotenuse. So we can use Pythagorean because we have the two sides and we're trying to find the hypotenuse. A squared plus b squared equals c squared. We know a and b. 10 squared plus 10 squared equals x squared. 10 squared is 100. 100 plus 100 equals x squared. Gives us 200 equals x squared. And then we don't want x squared, we want x. So we square root both sides. We get x equals the square root of 200. And then it says give an exact answer, which means we don't want to plug this into our calculator because it's not a perfect square. So that would give us a decimal answer, but we want to simplify the radical. Reminder about simplifying radicals, it's a square root, so we need a list of perfect squares. 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, 9 squared 81, 10 squared 100, 11 squared 121, 12 squared 144, etc. We need to find the biggest perfect square that can divide our radicand, which is 200. The number that divides it could only be at most half of 200, which is 100. And if we look in our list, 100 is actually a perfect square, so that would be the number we use. So we get x equals the square root of 100 times 2. And then we can take the square root of 100 because it's a perfect square. So we get x equals square root of 100 is 10, and then square root 2 centimeters. That brings us to the end of the first lesson for Chapter 2.